Hi all. For this second video, we're going to introduce a new distribution that we need to use for a new type of hypothesis test that we're going to perform. So we're going to go back to this idea of testing claims about means. In a previous unit, we learned we can test claims about a single mean using a z or t-test, and we can test claims about a difference between two means, so we can compare two different averages using a z-test or a t-test with a modified test statistic. The question is, what happens when I want to compare more than two groups, more than two averages? Suppose we want to know if there is a difference in one or more of the means between three groups. One way we could tackle this is by testing the difference between two means for every possible pair of means. And if I have three, I'd have to test 1 versus 2, 2 versus 3, and 1 versus 3. That's 3 hypothesis tests. If we're comparing more than 3 means, that list of hypothesis tests gets even longer. This can become unwieldy very, very quickly. The question is, as a statistician, is there a faster way to compare more than two means? And the answer is yes. Yes, there is. Instead of testing each pair of means separately, we're going to compare all of them at once using a process called analysis of variance. And it's called analysis of variance because I'm going to compare several means at once, not by looking at the means themselves, but by looking at their distributions and the spread of those distributions, because variance is one measure of spread. We shorten this to ANOVA for analysis of variance, and it's a type of hypothesis test that's using a new distribution, the F distribution. So we're going to look at properties of the F distribution, and we're going to learn how to find values for the F distribution using a table, because most calculators don't have this distribution programmed into their memory. So first, let's start with some facts. The F distribution looks familiar. This picture looks an awful lot like the chi-squared picture. You'll notice that the graph starts at 0 and goes to the right, meaning it has a minimum value of 0. We can also see that this distribution's skewed just by looking at the picture. So we know this distribution is going to be right skewed. The mean is further to right than the median. Just like our chi-squared distribution, it is a family of curves. Unlike chi-squared, this guy has 2 degrees of freedom. Just like chi-squared, he's greater than or equal to 0. And as those degrees of freedom get larger, this curve will also approach the normal distribution, just like the chi-squared distribution did. There are 2 different degrees of freedom that determine the shape of the F distribution. The first one is called dF numerator, the degrees of freedom for the numerator. And it's equal to k minus 1, where k is the number of samples or the number of means that we're comparing. So if I'm comparing 3 means, 3 minus 1 is 2. The degrees of freedom for the numerator is 2. The other one is dF denominator, and it's equal to n minus k, where n is the total number of sample values across all samples. So if I have 3 samples, I'm going to add the sample size for 1 plus the sample size for 2 plus the sample size for 3, and that's going to be that lowercase n. So typically what happens is that the numerator degrees of freedom is small, the denominator degrees of freedom is going to be bigger, because it's based on bigger numbers. So we're going to find the degrees of freedom for an F-test, and then we're going to look at how to find the test value for it using the F distribution. So we have 4 sports teams took a random sample of players regarding their GPAs for the last year. The results are shown in the table below. So I know to find my degrees of freedom, I need 2 values. How many samples? 4, basketball, hockey, baseball, lacrosse. And I need to know the sample size for all of the samples. And looking in that data table, I can see each of the 4 sports has 5 data values in it. So 5 plus 5 plus 5 plus 5 is 20. So K is 4, N is 20. I know that the degrees of freedom for the numerator is K minus 1. So 4 minus 1 is 3. And I know that the degrees of freedom for the denominator is N minus K. So 20 minus 4, which is 16. If I wanted to find the F value that goes with degrees of freedom 3 and 16, I'm going to go, hang on a second here, to table H, which is the table for the F distribution. And you'll notice, zoom in here, the degrees of freedom for the denominator are this way. The degrees of freedom for the numerator are along the top. So the numerator gives us the column, the denominator gives us the row. And so we know that we had degrees of freedom for the numerator, which was K minus 1. 4 minus 1 is 3. And then we had degrees of freedom for the denominator, which was 20 minus 4, which is 16. So I'm looking for column 3, row 16. So column 3, row 16, and I'm looking for where those intersect. So 3 is going to take me this way. 16 is going to take me this way. And I cross right here. So the F value for degrees of freedom 3 and 16 for a level of significance of 0.05 is 3.24. The complete table for the F distribution is going to be posted in Canvas, and you'll notice that it's multiple pages long because we need a different table for every possible alpha value. We're primarily doing problems where we've got 0.05. Your test for week 7 is only going to use 0.05 just for simplicity. But as you're working through the homework, you may notice you'll have to pull from other tables. So make sure when you're doing your homework that you're on the appropriate page. You want to make sure that you're in the table for F that matches the level of significance of your test. All right, if you have any questions about what you just saw, feel free to email me or drop into office hours. Otherwise, I'll see you in our next video, which is going to go through how to perform a test using ANOVA.